Welcome to our latest video on the topic of colour in transition metal ions and complexes. This video is suitable for A-level students. By the end of this video lesson, you should be able to explain how ligands cause d orbital splitting, leading to transition metal complexes being coloured. You should also be able to understand why different complexes have different colours, and be able to explain why complexes containing the copper 1+ and scandium 3+ ion are colourless. Now, in previous lessons on this topic, we've learnt that the chemical properties of transition metals are that they have variable oxidation states, they have catalytic properties, they have the ability to form transition metal complexes, and they form coloured compounds. And in this lesson, we're going to look at the reasons why they form coloured compounds. Now, we're going to learn in this lesson that the colour is to do with the transition metal complex that forms. And to help us understand this, we're first going to recap what we mean by the term transition metal complex. Now, in previous lessons, we've learnt that transition metals are defined as elements which have either atoms or at least one stable ion with partially filled d orbitals. They form small ions with large positive charges and have many orbitals available for bonding, many of which are empty. Now, we've learned previously that molecules or ions that contain lone pairs of electrons can surround the transition metal ion and form coordinate bonds with its empty orbitals. These molecules or ions are called ligands. Now, we've learned previously that the combination of the transition metal ion and the ligands is called a complex or complex ion. Now, examples of ligands that can surround transition metal ions are shown on this slide, and you'll notice that they all have lone pairs of electrons that can form coordinate bonds to vacant orbitals on the transition metal ion. Now, in a previous lesson, we've learnt that transition metal complexes are very often octahedral or tetrahedral, and examples of transition metal complexes are shown on this slide. Here are two complexes that the cobalt 2+ ion forms when it's surrounded by different ligands. If it's surrounded by water ligands, it has an octahedral shape, as shown on the left hand side here, and if it's surrounded by chloride ions, it forms a tetrahedral shape. Both complexes have cobalt at the centre of the complex, and the oxidation number of cobalt for both of these is +2. Now, we've learned previously that the coordination number is the number of coordinate bonds that form from ligands to the transition metal ion. So, in the first complex ion here, we have 6 coordinate bonds forming, one from each water molecule, and the coordination number is 6. And in the second example here, we have 4 chloride ions forming coordinate bonds to the cobalt, so the coordination number is 4. Now, in the examples that we come across during the WJC syllabus, each ligand forms one coordinate bond to the transition metal ion. Now, because of this, we can simply view the coordination number as the number of ligands that surround a transition metal ion. But really, the definition should be the number of coordinate bonds that form to the transition metal ion within a complex. Now, in other exam boards, students come across ligands that form multiple coordinate bonds to a transition metal ion, and therefore it's important to be aware of this definition. Now, the two transition metal complexes shown on this slide both give rise to coloured compounds. For example, the COH2O6 2+ ion is pink in colour, and the COCl4 2- ion is blue in colour. Now, during this lesson, we're going to learn that transition metal compounds are coloured because of the presence of these transition metal complexes. It's these complexes that give transition metals their different colours. And in this lesson we're going to look at examples of transition metal complexes and explore the reasons why different transition metal complexes have different colours. So let's start by looking at some examples of transition metal complexes and the different colours that they exhibit. Now, transition metal complexes are nearly always coloured, with almost every possible colour being observed in the wide range of complexes that exist. And it's important to stress that it's the formation of the complex which leads to the colour, and in the absence of any ligands around the metal ion, the compound would be colourless. Now on this slide are examples of transition metal complexes that either have octahedral shapes or tetrahedral shapes and the different colours that they exhibit when they're present in compounds. So for example, the presence of an FeH2O6 2+ ion gives rise to a pale green colour, while the presence of an FeH2O6 3+ ion gives rise to a yellow colour in compounds. A CuH2O6 2+ ion causes compounds to have a blue colour, while the presence of a CrH2O6 3+ ion gives rise to a dark green colour in compounds. A COH2O6 2+ ion, which we've just seen a few slides ago, gives rise to a pink colour in compounds. Now also shown on this slide are tetrahedral complex ions. So for example, the CuCl4 2- ion gives rise to a yellow-green colour, and the CoCl4 2- ion gives rise to a blue colour. Now the most popular shape for complex ions is octahedral, but you will also come across tetrahedral complexes in this topic. Now it's important to stress that at A level you are only required to be able to explain the colour of octahedral complexes. You will not be asked to explain why tetrahedral complexes give rise to different colours, only octahedral complexes. So to help us understand the different colours in different transition metal compounds, we're going to first look at the most famous transition metal compound that exists, copper sulfate, and explain why it's blue. Now the blue colour in copper sulfate is caused by the presence of this transition metal complex, CuH2O6 2+. It's this ion that causes the colour. Now copper has an electron arrangement of 4s1 3d10. And you remember that copper's electron arrangement is irregular because it takes the opportunity to have a full D shell by using one of its 4s electrons. And remember, the full D shell is a more stable arrangement. Now the copper 2+ ion is 3d9 because when the copper 2+ ion forms, one electron is lost from the 4s orbital and one from the 3d orbital. So I'm putting in the 9 electrons here in the 3d orbitals. Now the copper 2+ ion has an electron arrangement of 3d9 and the 9 electrons are located in 5d orbitals that are all the same energy. We use the term degenerate. That means they're the same energy. Now the colour is caused by the presence of CuH2O6 2+. And when water molecules surround the copper 2+ ion, the 5d orbitals no longer are the same energy. This is because of repulsion. Water molecules have electrons, and so do the copper 2+ ion. And when water molecules approach the copper 2+ ion, there is repulsion, and this leads to a splitting of the d levels, with 3 3d orbitals having lower energy and 2d orbitals having higher energy. Now the difference between these d levels in terms of energy is described as delta E. Now the reason copper sulfate is blue is that an electron can be promoted from a lower energy level to a higher energy level, It's called a DD transition, and this happens when copper sulfate absorbs light in the visible region. Now, the reason that copper sulfate is blue is because it's absorbing light from the red end of the spectrum and reflecting blue. Now, the actual frequency of light that copper sulfate absorbs is actually yellow light. Now, the colour you see is the colour not absorbed. It's the colour reflected. So if we look closely at this slide, we can see that the frequency of light that is absorbed corresponds to yellow light, is from the red end of the spectrum, and this causes an electron to be promoted from a lower D level to a higher D level. Now, the colour of the transition metal complex depends on the nature of the metal ion, its oxidation state, and the nature of the ligand attached. And this is because it's all down to the repulsion that exists between the electrons in the transition metal ion and the electrons on the ligand. The amount of repulsion determines the energy gap between the D levels. So you have to remember that the colour is caused by transition metal complexes. When ligands surround a transition metal ion, the repulsion between the electrons on the ligands and the electrons on the transition metal ion causes the d orbitals, the d levels, to split, and this split in energy, the energy gap between the lower d orbitals and the higher d orbitals, determines the colour. This is because electrons can be promoted from lower energy levels to higher energy levels if the compound absorbs visible light. And when it absorbs visible light, the colour you see is the colour not absorbed, the colour reflected. So the reason copper sulfate is blue is nothing to do with the sulfate ion, but all to do with the presence of a CuH2O6 2+ complex or ion, and the presence of this complex causes D levels to split and the compound absorbing light in the visible region and DD electron transitions. Now we can illustrate this by taking some copper sulfate and removing the water that's attached to the copper ions. Now we do this by adding a dehydrating agent, and a powerful dehydrating agent is concentrated sulfuric acid. Now when we add concentrated sulfuric acid to copper sulfate, the blue copper sulfate colour will gradually turn to a white colour because we are removing the water ligands, and it's the water ligands that cause the colour in copper sulfate. It's these ligands that surround the copper 2+ ion and the repulsion because of this that cause the D levels to split and therefore the DD transitions to take place. So to summarise, the colour of these complexes is caused by DD electron transitions, and the amount of energy between the lower and higher energy d orbitals determines the colour of the complex, as it's this split in energy, delta E, which varies. So does the frequency of light absorbed, which leads to different colours for different complexes. Now, some ligands cause more repulsion than others, and that's why the delta E value will vary depending on the ligand. Now, it also depends on the transition metal and the transition metal oxidation number, because what determines the splitting is the repulsion between the electrons on the transition metal ion and the electrons on the ligand. And having a different transition metal having a different ligand and having a different oxidation number on the transition metal will all cause different amounts of repulsion. Now, some transition metal complexes are, however, colourless. This is down to them having either empty or full D shells, so that DD electron transitions cannot take place. For example, copper-1 complexes, Cu1+, have a full 3D shell. So therefore, no DD transitions can take place. Now similarly, scandium forms colourless complexes as it can only form Sc3+ ions with an empty 3D shell. Therefore, once again, no DD electron transitions can take place, and it's these DD electron transitions that cause the colour in complexes. Now, in the case of zinc, you will remember that zinc is not classed as a transition metal as it doesn't have an atom or a stable ion with a partially filled D shell. It also cannot have DD electron transitions, as zinc's only ion, Zn2+, is 3d10. So for this reason, zinc doesn't have coloured compounds. Its compounds are white when they're solids, and it forms colourless solutions. Now, our evidence for DD electron transitions comes from spectroscopy. And if we pass light through these complexes, we can measure the wavelength that absorption occurs. Now, for the CuH2O6 2+ complex, light is absorbed at a maximum wavelength of 810 nanometers, which occurs at the red end of the spectrum. And that's why copper sulfate that contains this complex or this complex ion is blue, because it's absorbing in the red end of the spectrum and it's reflecting blue. So you'll notice from this spectrum that there is no absorption in the blue end of the spectrum. Now, when we change the ligand and we swap some of the water molecules for ammonia molecules, we have a different amount of repulsion that exists between the transition metal ions electrons and the ligands electrons. And therefore the DD level splitting is different. Now, the maximum absorption is occurring at 610 nanometers when we have ammonia ligands here. And this causes a deeper blue colour. Now, the fact that this absorption occurs at a lower wavelength when we have ammonia ligands means that the splitting energy is higher. And this is because the relationship between energy and wavelength is as follows. Energy is inversely proportional to wavelength. The bigger the wavelength, the smaller the energy. The smaller the wavelength, the bigger the energy. So therefore the splitting energy is bigger here because the absorption occurred at a smaller wavelength. So now let's test your understanding of this with some practice questions. So here's our first practice question. Read through the question, pause the video, have a go at it, and then we'll go for the answers. So this first question says that cobalt forms a range of complex ions. Two of these are COH2O6 2+ and COCl4 2-. And it's asking you to draw the structures of the COH2O6 2+ and COCl4 2- ions. Now this is a 2-mark question, so there's 1 mark for each correctly drawn structure. Now for this you have to realise that the COH2O6 2+ ion is octahedral in shape, and the COCl4 2- ion is tetrahedral in shape. So to get the marks, your diagrams should look like this. you should use solid wedges to represent bonds that are coming out towards you, and dashed lines to show bonds that are going away from you into the page. Now it's also important when drawing the COH2O6 2+ ion that bonds come from the oxygen, not the hydrogen in water, because it's the oxygen that has the lone pairs of electrons that form the coordinate bonds to the transition metal ion. Now this is a 2-mark question, 1 mark for each correctly drawn structure. So for part B, you're asked to explain why the COH2O6 2+ ion is coloured. Now you should know that this complex has a pink colour. So the first thing we need to do is work out the electron arrangement for the cobalt atom. Now the cobalt atom has an electron arrangement that ends in 4s2 3d7, and the cobalt 2+ ion has an electron arrangement that ends in 3d7. So I'm going to put in these 7 electrons into the 5 d orbitals here, and the d orbitals are all the same energy, they're degenerate in this cobalt 2+ ion. Now the pink colour is caused by the presence of the COH2O6 2+ ion or complex, and when water surrounds the cobalt 2+ ion, the repulsion causes the d levels to split, and all I've done here is show the first 3 orbitals having lower energy and the last 2 orbitals having higher energy. Now the reason this complex gives rise to a pink colour is because the complex absorbs light in the visible region and an electron is promoted to a higher d level. Now the frequency of light that's absorbed corresponds to the blue end of the spectrum. So it absorbs blue and reflects red or pink. So to get these marks, you need to talk about the ligands causing d orbitals to split into 3 lower and 2 higher energy levels. You get the second mark if you said that electrons absorb energy and are promoted to a higher energy level. So by absorbing light, the electrons get promoted to higher energy levels. And then you get the third mark for the idea that the colour seen is the colours not absorbed. So the reason that it's pink or red in colour is it's absorbing blue light from the blue end of the spectrum, and it's reflecting red or pink. So now have a go at our second practice question, and this comes in 3 parts, and part 1 and 2 are shown on this slide, and the final part is on the next slide. So read through the question, pause the video, have a go at the first 2 parts of this question, and then we'll have a look at the next part of the question. So here's the final part of this question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So now let's go for the answers to question 2. So the first part of this question says, state what is meant by a ligand. So this is a 1-mark question, and a ligand is a species, it's a molecule or an ion with a lone pair of electrons that can bond to a metal atom or ion. And if you said that, there's 1 mark. And for part 2, you're asked to draw the structures of CuCl4 and CuH2O6 2+. And you have to realise here that the CuCl4 has a tetrahedral shape, and the CuH2O6 2+ ion has an octahedral shape. Now there's 1 mark here for each correctly drawn shape. Now question 2b states that a solution containing CuH2O6 2+ ions is blue. Explain the origin of this colour, and this is a 3-mark question. Now when answering these sorts of questions, it's best to draw a diagram. So in my diagram, I'm going to draw the electron arrangement for the copper 2+ ion, which ends in 3d9. And then I'm going to show the d level splitting, with 3 d orbitals having lower energy and 2 d orbitals having higher energy. And I'm going to put in the electrons in these orbitals. Now these d levels split because of repulsion that exists between the ligands electrons and the transition metal ion electrons. Now the colour is caused by electrons absorbing light from the visible region, and this causes an electron to be promoted to a higher energy level, a higher d level. Now the colour you see is the colour not absorbed. So the reason that we see a blue colour is because light is being absorbed from the red end of the spectrum, and this is causing the electron to go from a lower d energy level to a higher energy level. It's causing an electron transition. So in this question, marks were awarded for the following. If you got across the idea that ligands cause d orbitals to split, with 3 lower d energy levels and 2 higher energy d levels, you get a mark. If you said that electrons move from lower level to higher levels by absorbing some frequencies of light, that idea gets you a mark. And if you got across the idea that light not absorbed gives the colour seen, you get the 3rd mark. So that concludes this video lesson. After watching this video, you should be able to explain how ligands cause d orbital splitting, leading to transition metal complexes being coloured. You should also be able to understand why different complexes have different colours, and be able to explain why complexes containing the Cu1+ and Sc3+ ion are colourless. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.